So it's my great pleasure to present some of the work that we've done recently on building hardware and software techniques to accelerate computation on encrypted data. I'm Daniel Sanchez, and I'm a professor here working in computer architecture. So specifically, we're looking at techniques to accelerate fully homomorphic encryption, or FHE, which is an emerging family of techniques that let us compute directly on encrypted data without decrypting it. And this is great because it enables offloading computation to the cloud with cryptographic guarantees on security. So if you have some function f of x that you want to perform as a client, but that function, let's say, is too expensive, you can encrypt the data x, send this encrypted data to the server will compute on this encrypted data without decrypting it, and then return an encrypted result that only you can decrypt. So even if the server is compromised, the attackers don't learn anything about the data. Now, nothing good comes for free. So there are two problems that prevent the wide adoption of FHE. The first one is that FHE is about 10,000 times slower than the native equivalent computing on unencrypted data. And so we can solve this with hardware acceleration. There's also a system-level problem, which is that even if we get that speed up from hardware acceleration and we enable new applications, FHE is extremely hard to program, so it requires a lot of expert knowledge of the intricacies of these crypto systems. And so we also can solve this programming complexity challenge with compiler support. Just to give you a high-level overview of the techniques that we have developed, as a key application, consider private inference. Suppose that you want to perform some deep learning inference on the cloud, for instance, because you're operating on some edge device that doesn't have a lot of compute power, or the model is too large to fit on the client, and the data must remain private. So here, I'm showing an example where the server is performing image classification. Now, the problem is that in state-of-the-art approaches will take about 20 minutes on a CPU to perform a single DNN inference, which is clearly too slow for many use cases. We've developed accelerators that can reduce this to much less than a second, so 250 milliseconds. And so this is about the round-trip time to the data center, so now you can accelerate inference on real time. Now, the other problem is taking a neural network like ResNet to FHE requires a team of experts taking several months to port this network, and I'll briefly explain why. We, through compiler techniques, have accelerated these to hours. So now you can code a neural network, train it, and then get very high performance equivalent to these very highly tuned implementations from very high-level tensor code. Now, I'm going to talk about specialized systems, and this highlights a problem with the way we're doing specialization today. So processors, as you've seen from the previous talks, now spend a lot of area on specialized units, not in general purpose cores. Just to give you a sense of this difference, if you look at a laptop CPU from 10 years ago, you see that most of the area goes to CPU cores and general purpose caching, and there's a GPU on the side, but most of the core or chip real estate is used for general purpose processing. The situation is basically reversed today, where if you look at a recent laptop chip, you can see that cores now take less than 10% of the area, and the GPU is actually the largest component here. But there's a lot of area here that's not labeled that's used for many other accelerators that are more special purpose than a GPU. Some of these is for neural network inference, similar to the techniques that Vivian mentioned. But there's many other accelerators in this chip. Now, the problem is that current accelerators are very, very rigid, and so they limit the algorithmic choice, for instance, the kinds of neural networks that you can accelerate. And so a key problem here is that FHE is a very rapidly evolving domain. And so we must build accelerators that are highly programmable so that we can support arbitrary programs. So what I'm going to do briefly in the rest of the talk is to give you a brief overview of how FHE computations work, as well as give you a brief overview of the hardware accelerators that we've designed to accelerate them. If I have time, maybe I'll talk a little bit about our compiler work. So FHE programs are basically circuits or static data flow graphs of operations on ciphertext. These are called homomorphic operations. So simply a homomorphic operation like a homomorphic multiplication or addition performs that operation on the data that the ciphertext encrypts. And so here you can see a simple circuit that performs A times A plus B. Now, data is encrypted, and you can't take runtime decisions on encrypted data. So you can't, for example, branch or have data-dependent control flow. And so as a result, this is not Turing complete. However, it is sufficient to implement many interesting classes of computations, things like machine learning inference, genomics, linear algebra applications, private information retrieval on databases, and so on. And so there's a wide range of applications that have been developed and adapted to FAT in recent years. Now, as a computer systems designer, as a computer architect, I like to differentiate the interface and the implementation of FAT schemes. Now, these techniques have fairly complicated details, but I will give you the computer systems view of how to understand what are the key parameters in these FAT schemes. Now, when we talk about an interface, generally the first thing that we describe is the data types, right, that some system supports, and then the basic operations. And in this case, for FAT schemes, at least for these crypto systems that support higher performance, they always work on vectors of values. And so different systems, different kinds of data for each element. So for instance, they might encode integers. We'll be seeing CKKS, which is an FAT scheme that's the state-of-the-art one that encodes fixed point values. And these are really large vectors. This is about 32,000 to 64,000 elements each. To encrypt these, you add some small random noise for security, combine it with a secret key, and produce a ciphertext. And its ciphertext is about the same size in number of elements as the number of elements that you encrypt, the number of plaintext elements in its vector, but the coefficients are much wider. And so there's a data blow-up here. Moreover, these are modular integers. So essentially what you end up is with polynomials, that is vectors of coefficients, that have very large, very wide integers modulo some value. So now, given these ciphertexts, FAT schemes let you perform 3 operations. These are addition, element-wise addition, element-wise multiplication, and element-wise rotation of the underlying values. And these operations are not just applying, let's say, multiplying, doing element-wise multiplication on the ciphertext. So for example, if you want to multiply 2 ciphertexts x and y, you need to take these polynomials, perform polynomial multiplication of pairwise of as shown in the data flow graph here, and then use pass one of these intermediate results through what's called a key switching algorithm, which is a pretty expensive auxiliary procedure that lets us restore the original encryption key, and then we end up with this polynomial here, or this 2 pair of polynomials that encrypts the product of the values encoded in ciphertexts x and y. Now, one note here is that these are polynomial multiplications, which are actually convolutions of their coefficients. If you're familiar in signal processing, you can do convolutions in the frequency domain using a fast Fourier transform. With modular arithmetic, there's a similar principle, so you can use number theoretic transforms, which lets you translate from the coefficient domain to an entity, transform domain, and then perform these multiplications element-wise. And so you can do multiplications of polynomials in n log n, but that means that we need to accelerate this entity operation. Now, an additional challenge here is that I mentioned before that ciphertexts start with some initial noise, and this noise is crucial for security. If you don't have noise, essentially you can give you 2 ciphertexts and you can recover the secret key. But the problem is that as you compute on these ciphertexts, the noise grows. And so you first can chop it off, essentially reduce the width of the coefficients and reduce noise that way. But eventually, we run out of noise budget, and we need to refresh the ciphertext if we want to keep computing. And so this is the shape of the bit width over time for the coefficients of our ciphertext. We start at some large bit width, and then we go down, 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 down. Eventually, we boot it back up, perform this bootstrapping procedure, refresh the noise in the ciphertext, and then keep going. The problem with this is that now we need to perform computations at multiple bit widths. And if you know about hardware design, this is kind of hard to do in a standard if I give you arbitrary widths. Now, there's one saving grace here, which is that we can use this residue number system, which essentially lets us represent, thanks to the characteristics of FAT, lets us represent wide integers modulo a large value by carefully choosing these large modulus as the combination of smaller, what's called residue polynomials that are much narrower. And so, we can, this actually makes operations simpler as well. And so the advantage here is that we can perform arbitrarily wide modular arithmetic with very narrow multipliers. Okay, so to summarize the characteristics of these systems are that, we have arbitrary computations on encrypted data. So this is just not a single application. Despite encryption being in the name of FHC, we actually don't accelerate the encryption process. What we want to do is accelerate the computation on encrypted data. There are many such programs that operate in computing on encrypted data, and we want to accelerate all of them. All of these homomorphic operations rely on arithmetic on very large polynomials that have modular values. These ciphertexts are really large. Sometimes they are megabytes or tens of megabytes. So data movement, as Vivian mentioned a couple of talks ago, is extremely important as well as in this domain. The saving grace is that the data flow, that is, the set of operations that we perform, is completely static because we don't have any dynamism in our algorithms. We know what we're doing, what operations we're performing ahead of time. And so we can use these to design very simple hardware and very efficient hardware. There's been about a decade of accelerators trying to accelerate these FHC computations, but they have substantial limitations. They were built for FPGAs. They yielded limited speedups. They only looked at some particular operations and deferred others to a CPU. So they were limited very quickly by Amdahl's law. But more importantly, they built, to get high performance, they built very highly specialized pipelines for essentially large algorithms. And so what we're going to do instead is build very high performance acceleration of the very basic operations in this domain. So let me show you what I mean by that. The first accelerator that we designed in this domain is a system we call F1. It's essentially a vector processor similar to a GPU. It operates on large vectors of data. The difference is that there are two operations. The difference with a GPU is that there are two operations here, entities, which I briefly mentioned before, and automorphisms, which are essentially structured permutations that are used to implement rotations that are not, basically they're all-to-all operations. And so it would be hard to implement in a GPU. So we need new techniques to support them efficiently. Other than this, we also need to very carefully design the system to reduce data movement. So we have an explicitly managed memory hierarchy that lets us maximize reuse, and it lets us exploit high bandwidth memory, as well as hide the latency of fetching these very large ciphertexts from main memory. Because we have this ability to know a priori what computation we're doing, we have a new way to statically schedule this architecture. Just to give you a little bit more detail, we give every component a fixed latency. We'll have an independent configuration stream for each component. And so then we basically let the whole program run in a distributed control, operating all of these functional units separately, which means that we have no scheduling hardware, no central scheduling hardware, no stall logic, no network routers, no dynamic decisions being taken. And this makes, reduces control overheads greatly. So, of course, the problem with this kind of static architecture is that we need a very sophisticated compiler to schedule these operations and produce a cycle-level schedule that obeys all of the dependencies. Okay, so let me jump right into sort of the key problem in designing efficient compute. As I mentioned, we have a vector data path. So here we have 128 chunks, but because 128 is kind of hard to draw, I'll draw 16. And this shows an entire vector, and so what I'll show is 4 instead of 128, because we need to have, when we actually have up to 64,000 elements per ciphertext polynomial, and so we need to process them in consecutive chunks. And so for element-wise operations, like vector additions and multiplications, this is very easy. You operate on 1 chunk per cycle, stream all of those, and that's no problem whatsoever. Problem is that, as I mentioned, entities and automorphisms have dependencies across chunks. So just to give you a sense, in an automorphism, this is the set of elements that you need to access every cycle if you're trying to output 1 chunk every cycle. And this makes them very hard to vectorize and pipeline. So what we figured out is that you can have very high performance transpose operations to enable these all-to-all operations to happen completely in parallel. I haven't talked about automorphisms yet, but as I mentioned before, these are the primitive that enables rotations. And essentially, forget about this complicated formula here. I'm just going to show this graphically. What this does is it lets you spread coefficients that are nominally consecutive by some factor, and then you go mod n once you sort of run over the length of the vector. So for example, automorphism 3 maps element 0 to position 0, position 1 to position 3, so it expands by a factor of 3. That's why this is automorphism 3. 2 to 6, and so on. Eventually, you run out of, for 16 elements, you run out of 16. And so for element 6, this goes back to, 6 times 3 mod 16, which is 2. And so you can see here that this permutation would be quite hard to do in one step. What we figured out is that if you do 2 different transposes, you can decompose these permutations into permutations within chunks across these transposes. So this shows that we can permute within each chunk, or do a permutation essentially of the columns, then we transpose, so columns become rows, then permute the rows, and then transpose again. And you can see that this implements the permutation that we had before. Not an easy insight, but once we had this, we showed that you could vectorize the whole pipeline. I'll skip, the details on entity units because they're a better understood domain, and it's known there that transpositions also help. Okay, so as I mentioned, we bear it all to the compiler, and so we need novel compiler techniques to actually produce a performance schedule. We do this over multiple steps, and so by dividing the complexity of the problem, we first have a simplified schedule where we focus on minimizing data movement from memory, and then we have a second, exact cycle level scheduler that produces the final refined scheduler. And this lets us overcome the limitations of schedulers for prior statically scheduled architectures, which can handle very large programs, and despite having decades of research, don't scale to our problem sizes. So we implemented F1. We basically wrote the RTL and synthesized all of their functional units and showed that with a chip of a fairly modest size and power budget on actually not a pretty recent process, it's a 14 to 12 commercial nanometer commercial process, we can get very high performance. So we get on a number of applications spanning machine learning, logistic regression training, database lookups, as well as this bootstrapping operation that I mentioned. We get speedups that are on average 5,000 times over the CPU, CPU with equivalent or similar area and power budgets. And so remember that I mentioned that there's a 10,000x slowdown, and so we can get, we can recoup a lot of this cost by doing hardware acceleration. Now, this is only part of the picture. So if you move to larger computations like deep neural networks, you need new techniques to actually accelerate those. And the reason is this bootstrapping procedure that I mentioned requires far larger ciphertexts. And so we designed a different accelerator called Crater Lake that is larger and scales to larger ciphertexts and the larger programs than F1. So there's 2 tricks to do this. First is to have actually a very simple logical organization. This is rather than a vector multi-core like F1 was. It's a very, very large vector uniprocessor. Problem is, how do you implement this? It wouldn't be feasible to implement this because you have these all-to-all functional units, but we figured out a way to make it scale, again, by figuring out how to do transposes at scale. So as a result, we can get another order of magnitude performance improvement over F1. So, given this, as I've hopefully convinced you that you can get very high acceleration degrees, I will skip all of the material on simplifying programming and just leave you with a conclusion, which is FHC suffers from high overheads and programming complexity, and so we can dramatically reduce these overheads through hardware acceleration, enabling new applications like private deep learning in the cloud. And a key component here is that we can achieve fixed function performance without sacrificing programmability. So still have the flexibility of a programmable accelerator while getting a near perfect resource utilization. All right, so that's it for today. Thank you.